Alright, Prop 37 says triangles which are on the same base and in the same parallels are equal to one another. So it's really similar to the last two propositions, but instead of talking about parallelograms with similar bases and between the same parallels, now we're talking just about triangles. And the idea is going to be very much the same. So we're going to use kind of what we know about parallelograms to prove this, and there is one step sort of towards the end that I think is not quite as logically rigorous as maybe we might want it to be, but it still makes intuitive sense. So let's get there. Alright, so imagine that we have our two triangles, ABC and DBC. I drew them very symmetrically. I kind of did that on accident. I didn't mean to, but you know, they don't have to be so symmetric. So in any case, suppose that we have ABC and DBC. Obviously, they share the base BC, and then A and D both fall on the same line, which is parallel to BC. That's the setup. And what we want to do is we just want to prove that ABC and DBC are equal. And here, the word equal is kind of being a little bit overloaded because, again, previously, whenever we talked about two triangles being equal, we oftentimes meant they're congruent. Here, we're not talking about congruence. We're talking about the area. So for any two triangles on the same base and in the same parallels, their areas are equal. And we, again, with what we know today, this is kind of obvious because the area of a triangle is 1/2 base times height. So both of these have the same base and the same height. Obviously, they're going to have the same area. And that's what we want to prove. So the first thing that we want to do is we want to just, well, what Euclid says is he says let AD be produced in both directions EF. He's just talking about this line up here, this parallel. He's just saying just extend it because we're going to form some new lines that connect with that line. In particular, we're going to plot point E such that BE is parallel to CA. So proof. First, we'll construct BE parallel to CA. Yeah. Okay. So I'll pull out my compass for this and see if I can get some precision. But maybe even just based off of that little line right there, maybe you can, if you want, you can try to see if you can prove this, finish out the proof. So we'll join about right there. Okie dokie. So there's my point E, and I'll connect BE. Whoops. A little smudge. It's not very obviously an E. That is an E. Yeah, there. That's a little bit clearer. It looks like a second grader wrote that. Right. And I suppose we should justify that. That was Prop 31 that allows us to make parallel lines like that. And similarly, we want to draw CF to parallel to BD. Which is, I guess, also Prop 31. I could have just written that all as one line, but I didn't. Right, so CF, F is going to fall somewhere over here parallel to BD. These are probably fairly similar lines in terms of length. Yeah, almost the same. Geez, I just made this so symmetrical. It was on accident, happenstance. I mean, it was a conscious accident, probably subconsciously it was intentional. It's kind of like how whenever I'm drawing, just like if I try to draw just like a generic triangle, it's really hard for me to make it scalene. It always comes out as either a right triangle or isosceles. I just can't help it, no matter how hard I try. Okay. So we've constructed BE parallel to CA. We've constructed CF parallel to BD. So what have we just constructed? Well, we've made two parallelograms. Then I'll say, so the two parallelograms we have are EBCA. I guess there are maybe other parallelograms in there, but the important ones are EBCA, and the other one is DBCF. They share a base, BC, and they fall between the same parallels. So we have a proposition that says something about parallelograms that have share the same base and fall between the same parallels. Namely, they're equal in area. That was prop, what was it, 35? Yep. Yeah, prop 35. Just double checking myself. Yep, prop 35. Right, EBCA is equal to DBCF. Okay, well, what else do we know? If we look at EBCA, notice that in EBCA, AB bisects it. So, and maybe I'll say, here's how I'll write it. Well, what does Euclid say? Because the way he says it and the way that I want to write it are a little bit different. Euclid says, moreover, the triangle ABC is half of the parallelogram EBCA, for the diameter AB bisects it. So the way I kind of want to write it, though, just kind of looking ahead of to where the logic is going, is I might say something like, then triangle ABC is equal to triangle ABE. Since AB bisects EBCA. And similarly, triangle DBC is equal to triangle DCF. Since DC bisects DBCF. Right, DC, yeah. And all of that comes from prop, what was it? 34. All right, well, what do we have then? We have that EBCA equals DBCF. So, in other words, ABC plus ABE, which is EBCA, is equal to DBC plus DCF. I don't know how to write this very smoothly, and because there's some details there that I want to fill in, because let me just say what Euclid wrote. So after pointing out that DBC is half of the parallelogram DBCF, and this is kind of, there's a line that's written in angle brackets, meaning that this line has been kind of added by later authors. It wasn't in Euclid's original elements, but he says, but the halves of equal things are equal to one another. That's the part that's in angle brackets. So it says, it concludes, therefore, the triangle ABC is equal to the triangle DBC, which is correct. But I kind of want to fill in some more details to really make that very clear. So I might say, maybe I'll say note. That sounds sophisticated. Note that EBCA is equal to ABC plus ABE, but we know that ABC is equal to ABE, so this is really ABC plus ABE is equal to ABC plus itself. And similarly, DBCF is equal to DBC plus DCF, which is really just DBC plus DBC. Okay, the video is starting to lag a little bit, but we know that EBCA is equal to DBCF, so it follows that ABC plus ABC equals DBC plus DBC. So what I might say then, just to make it really kind of like obvious, it's modern notation. The Greeks wouldn't have really thought of it this way, but I might say ABC plus ABC is 2 times ABC, and that's equal to 2 times DBC. So we get that triangle ABC equals triangle DBC, which is what we wanted to prove. So QED, therefore, etc.